Hello guys, good morning. Good morning to all of you. Today we'll be discussing particle in an infinite asymmetric potential well. This is one of the most important topics in quantum mechanics and many questions come from this. Previously many questions came from this topic and in future also you can expect a lot of questions in the upcoming exams. So we'll cover this topic today. Before I start, let me know if everything is all right. So we'll cover this topic. Is audio, video, everything all right? So particle in an infinite asymmetric potential well. So before going into that, let's just cover a small topic from the last topic, the tunneling effect. Actually, we mentioned about this term, tunneling effect. Let us know what it exactly is. So you see, in general, tunneling effect consists of the propagation of a particle through a region where the particle's energy is smaller than the potential energy E less than V. So what happened? You imagine that you have a wall in front of you and you are standing here. Your energy is not enough to cross this wall. So classically it is not possible to find you on the other side of the wall because the wall is high enough. But when we go for the quantum region, when you go to the microscopic level, if a particle is there whose energy is less than this step potential, still there will be a finite probability to find a particle on the other side. So this effect is known as the tunneling effect. So tunneling effect is observed only in the quantum region. Classically it is not possible, quantum mechanically it is possible. So the condition is E less than Vx. When the particle's energy is less than the potential, then you will see tunneling effect. Classically this region defined by x1 and x2. You see, x1 and x2. It is forbidden to the particle where its kinetic energy would be negative. The point x1 and x2 are known as the classical tunneling points. We have already talked about it. Quantum mechanically, however, since particle displays wave feature, the quantum waves can tunnel through the barrier. Classically, particles cannot pass through, but quantum mechanically, the particle can tunnel through this barrier. Good morning, Murli. Let us now go to this main topic, the infinite square well potential. The overall topic name is the infinite square well potential. It has actually two parts: infinite asymmetric square well potential, and the second part is symmetric. Today we will be covering this asymmetric. Asymmetric means when you take the wall extending between 0 to L. This is asymmetric case. Symmetric means it will be something like this. The 0 will lie at the middle. So let's say L by 2. This is minus L by 2. Total is remaining L. But 0 is at the center for the symmetric case. Okay. So the first case which we will be discussing is the particle in an infinite asymmetric potential well. Particle in an asymmetric infinite potential box or potential well, whatever you say. So what kind of potential we consider here? We say that there is a particle which is confined into a region like this. Okay, like this. This is your x-axis and this is the potential part. like this. So you can imagine that we are plotting v of x versus x. And the particle is restricted between 0 to, let's say, a. The particle is here of mass m. So you see the particle can move back and forth into this region, and it is not allowed to go outside it. Okay, this is infinite potential well. So particle must restrict its motion inside the well only. Now if you define this potential mathematically, the potential is defined in this way. The potential of the one dimensional box is defined as, so you can see v of x, it is equals to 0, here it is 0, where between 0 to a, and it is infinity otherwise, whether you consider x greater than a or you consider x less than a, v of x is infinite. Now we got this potential, so we can use the Schrodinger equation to get the solution. Okay, so we will be using time independent Schrodinger equation. We have two regions, sorry, x, this will be x less than 0. So we are going to use time independent Schrodinger equation. The first region which we will be applying it for, look, x less than 0, x greater than 0, and between 0 to a. So these are the three regions you need to consider. Now you see the potential is infinite for x less than 0 and x greater than 0, x greater than a. So the wave function must vanish there. So we can just write it in this way, since the potential is infinite for x less than 0 and x greater than a, hence the wave function vanishes there. If there is infinite potential, the wave function will vanish. Wave function vanish means what? If there is wave function, the feature of wave function means you have some probability to find the particle. Now as it is infinite, under no situation you will get the particle. If particle cannot be found, if particle cannot be found, means wave function must vanish. Particle and wave are interrelated, right? If wave function vanish, means particle is not possible to find. The particle is only possible to find between 0 to a. So we have to solve this Schrodinger equation between 0 to a. Here you can also add a line, because the probability to find the particle in those region is 0. Now we are considering the region between 0 to a. So for 0 to a, you know, v of x is equals to 0. Therefore from the time independent Schrodinger equation, we get? You see the Schrodinger equation minus h cut square by 2m d square psi by dx square plus v psi v is 0. So you can also write, if you want to do one step, you can do one step, but it is okay. E psi. So it will come out in the usual form, the way we have already done for step potential. This will be twice me by h cut square psi is equals to 0, or simply we can write d square psi by dx square plus k square psi equals to 0, where this k square root of twice me upon h cut square. So if you know this, then we can write the solution in this way: a to the power I kx. Okay, or let us write some other term, a prime, a to the power I kx plus b prime e to the power minus I kx. So this can be alternatively written as, in terms of sine and cos, a sine kx plus b cos kx. Now we need to find out these constants a and b using the boundary condition. What are the boundary conditions? The boundary conditions are that the wave function of the particle must vanish at the boundary, right? Because the potential is infinite there. So at x equals to 0 and x equals to a, the wave function must vanish, and the derivative as well. The derivatives also should vanish. So let us use that boundary condition. You can write now wave function must vanish at the boundary. Okay. And using that, psi at x equals to 0, psi at x equals to a, it must be 0. So psi at x equals to 0, if you put, so a plus b equals to 0. Okay, so 0 equals to a sin kx, so 0 plus b cos kx, so b. So we get b is equals to 0. So one constant is gone, and hence we can write that psi of x is equals to a sin kx. Now we have to find out a. So let us use this boundary condition that psi of a is equals to 0. Psi of a is equals to 0 means 0 is equals to a sin k a. So for what value of sin k, this is 0. 0 is sin n pi. Okay, so k is equals to n pi by a, where n is equals to 0, 1, 2, 3 and so on. But here is a twist. N is equals to 0 value, although it is mathematically allowed, physically here not allowed. Because if you consider n is equals to 0, if you consider n equals to 0, then this wave function vanishes. Psi of x is equals to 0. Therefore, n is equals to 0 is not allowed. Okay. Hence, the allowed values of n are n is equals to 1, 2, 3 and so on. N equals to 1 will be ground state, n equals to 2 will be first excited state, n equals to 3 will be second excited state and so on. Now, let us calculate the energy eigenvalues. What will be the energy eigenvalues? Energy eigenvalues is very easy to find out, because you see we have seen that k is equals to square root of twice me by h cut square, right? Now, the value of k we have just found out, n pi by a twice me by h cut square. From this we can just, if I am writing k is equals to n pi by a, we can also write en here. So, en is equals to, let's keep it root. So, en is equals to, you have to take a square on both sides, n square pi square h cut square divided by twice m a square. So, this is the expression for energy eigenvalue. So, you can see by putting n is equals to 1, you get ground state, n equals to 2 first excited state, n equals to 3 second excited state, and from this you can easily see that en is the energy eigenvalues. ENs are the energy eigenvalues which are discrete. Discrete means not continuous. Like if you see the first ground state will be pi square h cut square twice m square. First excited state will be 4 pi square h cut square by twice m square. So, it is not continuous, it has some difference between them. So, it is discrete. Okay, just a moment. Okay, let us go for the energy eigenfunction. Eigenvalues. Now, eigenstate. Eigenstate, if you consider, so what we have till now, we have got, let's say, psi n f x. It was a sin kx. So, a sin k is n pi by a, so n pi x by a. This one we have got. If you want to write it in a more detailed way, you can write it a sin kx, k is equals to n pi by a. Now, we have an unknown constant a. For this wave function to be an allowed wave function, this wave function must be normalized. So the value of A can be found out using the normalization condition. If n is equals to 0, k also 0, momentum of the particle also 0 in the region 0 to A, but we are considering free particle inside the box, that is why it is physically not acceptable. Sorry. No. Dekho, what is the meaning of free particle? We are not considering free particle in the box. Whenever we are applying some potential, non-zero potential, it is no longer a free particle. So here this particle is not a free particle. Free particle is when Vx is 0 everywhere. But here you see Vx is 0 only on this part 0 to A. It is infinite otherwise. So free particle case is only one case where V of x is 0 everywhere. Otherwise we cannot say any particle to be a free particle. This is the first part needs to be clarified. Now n is equals to 0, momentum of the particle will be 0. But quantum mechanically, why n equals to 0 is not allowed? Because of uncertainty principle. As per uncertainty principle, the particle cannot sit idle. So if n equals to 0 is momentum is 0. Momentum is 0 means what? The particle is resting somewhere. But quantum mechanically that is not possible, because Heisenberg uncertainty principle says that there must be some uncertainty in its position, delta x, then delta px greater or equals to h squared by 2. If the particle is having 0 momentum means delta x is 0. So which is against Heisenberg uncertainty principle. So there will always be, the particle is always moving. Okay. So that is why there is nothing like 0 energy. Even at the ground state, the particle has some energy, that is n square pi square h squared square by twice m a square. I hope this clarifies your doubt why n is equals to 0 is not allowed. Because if you take n equals to 0, energy will be 0. But the particle cannot sit idle. So it will obviously have some kinetic energy because of the uncertainty principle. Now to calculate the value of A, we need to utilize the normalization condition, that is minus infinity to plus infinity psi n of x mod square dx is equals to 1. Now the wave function is valid between 0 to A. So we are writing 0 to A square sin square n pi x by A equal to 1. And if you calculate this, what value of A will get? So you can just take half into 2 sin square n pi x by A dx equals to 1. 2 sin square x is equals to 1 minus cos 2x. Okay. So this part will give you sine. So that will automatically vanish, because the derivative integration of cos will give you sine, and if you put the limits, it will automatically become 0. The second term will be 0. The first term dx will give you A. So it is A square by 2 times A is equals to 1. So A is equals to square root of 2 by A, and from this we get the value of psi n of x square root of 2 by A sin n pi x by A. So this is the energy eigenstate for a particle in a one-dimensional box. So by putting the values of n, we get different state. If you put n is equals to 1, you get ground state. If you put n equals to 2, you get first excited state, n equals to 3, second excited state, and so on. Is your doubt clear, Murli? And these states are orthonormal. Okay. These sin x are orthonormal states. The orthonormal states the orthonormal condition is given by 0 to A psi n star psi m dx delta nm. Look, any function we can write with the help of this psi nx. Any function f of x can be expressed in terms of psi n of x. How to express it? We can use this expression: f of x is equals to sum over n is equals to 1 to infinity Cn psi n x. Now using the orthonormality condition, we can find out Cn, where this Cn is equals to psi n star f of x dx. So you just use the orthonormality condition to evaluate Cn. So if you multiply psi n star on both sides and take integration, this term, the right hand side will be free and it will turn out to be Cn, and the left hand side psi n star fx dx. And this is clear. Now let us try to understand the first few states. So what we have a situation like this. Like this. This is the case of an infinite potential well. The well is extending between 0 to A. The midpoint of it will be A by 2. Okay. And this is an infinite potential. So it is going to infinity. Let's say we are plotting the wave function psi of x, and this line is x. If I am talking about the ground state, what will be the ground state? Let's say this is the ground state. First excited state, second excited state. What will be the first excited state? So what is the ground state first? N is equals to 0 if you take, we get sorry, n equals to 1, the ground state will be E1 n square, so 1 square pi square h cut square divided by twice m a square. N is equals to and the wave function will be psi 1 square root of 2 by a sin n is 1, so pi x by a. Now let us take n is equals to 2, energy will become 4 means 2 square pi square h cut square by twice m a square, and the corresponding wave function will be psi 2 of x square root of 2 by a sin 2 pi x by a. If you choose n is equals to 3, you get E3 9 pi square h cut square by twice m a square, and the wave function psi 3 of x square root of 2 by a sin 3 pi x by a. Now, as I told you, if you remember one theorem which we gave you in the very beginning, very first class of this potential, that whenever n starts from 0, it has nodes, the system will have node n minus 1. Node means number of times the wave function vanishes. If it is 0, number of nodes, sorry, it is n. And if n starts from 1, the number of nodes will be n minus 1. Do you remember this? We have told you this one. So here you see the n value starts from 1. So number of nodes will be n minus 1. So for the ground state, what will be the number of nodes? 1 minus 1, 0. So it will not vanish anywhere in between 0 to a. Here the wave function square root of 2 by a sin pi x by a will be like this. You can put x equals to 0, it is giving you 0, x equals to a, it is giving you 0. If you put x is equals to a by 2, so you get sin pi by 2, that is 1. So that is why it is becoming maximum at a by 2. Now for n is equals to 2, what is the number of nodes? 2 minus 1, 1. So it will vanish 1 times. How? It will be like this. And as you can see, it is becoming maxima at a by 4. Okay, if you choose a by 4, it gives you sin pi by 2. Okay, so that is why you get this one. So it has one node, but there is no node here. Psi 3, how many nodes it should have? 3 minus 1, 2. So it means it should vanish 2 times. So it will vanish in this way. It will be like this. So it is vanishing here and here. So it is vanishing 2 times. It has 2 nodes. So these are the wave function, first few wave function. This wave function for the ground state. This is for the first excited state, and this is for the second excited state. Is it clear? Now this n is equals to 1, the ground state energy, you can consider it to be 0 point energy, lowest one. Now the lowest one, to understand this lowest value of energy, let us consider 3 systems and try to find out. So you will see, as you go from macroscopic level to microscopic level, means you are going from bigger object to very smaller object, and you will see this 0 point energy will be significant towards the microscopic level. Let me give you one example to understand this. Let's write a problem. So we have to calculate the 0 point energy. 0 point energy means you can understand for the time being the ground state energy. 0 point energy for a particle in an infinite potential well for the following 3 cases. So 3 different cases you will consider to understand it better. The first case, it's a macroscopic case, a 100-gram ball, confined on a 5-meter long line. So this is also the case of one-dimensional box, but here the object is 100 gram, means macroscopic. Second one, it is an oxygen atom confined to a 2 into 10 to the power minus 10 meter lattice. So we are narrowing down the dimension. And finally the third case, even smaller, there is an electron confined to a 10 to the power minus 10 meter atom. So you can see we are systematically decreasing the size. Firstly 100-gram ball, then oxygen atom, then an electron. So we'll see the difference in their 0 point energies. First of all, if you consider the first case, a 100-gram ball, so mass m is equals to 100 gram and a is 5 meter. Okay, so 100 gram means 0.1 kilogram. So the ground state will be n square pi square h cut square by twice m a square. This is the formula we get. So if you put all the values, what you get, this is 3.14 square, so approximately 10, you can imagine it. H cut square, so approximately 6.6 into 10 to the power, you can put approximate values for the timing. So 10 to the minus 6 to 8 will come, divided by 2m, mass is 0.1 kilogram and a is 5 meters, so 5 square. So this will come around 2 into 10 to the power minus 68 joule. If you divide by the electronic charge, it will give you in electron volt. So this will become 1.25 into 10 to the power minus 49 electron volt. So you can see this is very small, negligible. So this energy is too small to be detected. So that is why macroscopically we do not feel the existence. Now if I consider the oxygen atom, H cut means we have to put 2 pi in denominator. Oh, all right. So we can just write, instead of 6.6, you can write 1.5, I think 1.55. Sorry, 1.05. Actually, the order we are observing, not exact calculation is required here. We are just observing the order, but to be to keep correctness is very important. Thank you, Karthik. Yes, 1.05. Now let's talk about the second case, an oxygen atom confined to a 2 into 10 to the power minus 10 meter lattice. Oxygen atom means we're talking about oxygen 16 atom. Okay, so you see, what is the mass of a oxygen atom? So you can consider the mass of an oxygen atom of the order of 16 atomic mass unit, 16 into 1.6 into 10 to the minus 27 kg. So for m value for oxygen atom, we can take this one. So what will be the value of E1, ground state energy, pi square h cut square by twice m a square. So put the value 3.14 square, 1.05 10 to the minus 34 square divided by 2 into m 16 1.6 10 to the minus 27 a, it is now 2 into 10 to the power minus 10 square. So this will give you around 0.5 into 10 to the power minus 22 joules. Converting into electron volt, this gives you 3 into 10 to the power minus 4 electron volt. So this is a better situation, right? 3 into 10 to the minus 4 electron volt. Now if we are going further into more microscopic level, if you are going for the case of an electron, for electron we can take the mass of the order of, look, 9.11 into 10 to the minus 31 kilogram. So almost we can take 10 to the minus 30 kg. Okay, so 9.11 approximately 10 into 10 to the minus 31, so 10 to the minus 30. So it is confined to a 10 to the minus 10 meter atom. So we can say that A is nothing but 10 to the power minus 10 meter. Now if you calculate the energy using this formula of pi square h cut square by twice m a square, you get something like this: 3.14 whole square, 1.05 10 to the power minus 34 square twice approximate. These are approximate result. Okay, so approximately 5 10 to the power minus 18 joule. This gives you approximately 30 electron volt. So you can see, as you are going from the macroscopic level to the microscopic level, this 0 point energy becomes significant. So this 0 point energy is important on atomic scale. So this energy is important at the atomic scale. For what is the binding energy of an electron in the hydrogen atom? Binding energy of a hydrogen atom electron is about 14 electron volt, but here it is 13, so it is important. So the 0 point energy is negligible for macroscopic object. Macroscopic means big. Macroscopic objects, but it is significant or important for microscopic object on the atomic scale for microscopic system. I hope this is clear. Now we have this well in this way. Okay, so this is the one-dimensional potential well. Zero to A. A particle is there inside. No issue in this. So particle is moving back and forth. So can you tell me at which location the particle is most likely to be found? What is atomic scale? Atomic scale means of the order of when you go to the order of an size of an atom. The size of an atom means in the angstrom level 10 to the minus 10 meters. So if you go down to that level, that region is called atomic scale. Okay, like if I am telling you that the height of a building, like the height of very big building, it may be maybe 800 meters or so. So you can say that it is on meter scale, you can take, or kilometer scale. Now as you go down, so if you are probing atoms, electrons, we can say it is atomic scale or nanometer scale, microscopic. Okay. Now this particle is moving backward and forward, back and forth in this way. So where exactly this particle is most likely to be found? When on an average, where this particle will lie? How can you find out? So to find out that, if you find out the expectation value of x for this particle, we can say that the particle is most likely to be in that position. So our target is to calculate the expectation value. Find the expectation value of x of the position of a particle trapped in a box of width A. Can you tell me where it should remain most likely? Is it near about 0 or near about A, or at the middle, or anywhere between this? Where? We do not know, but we are expecting that it should lie in the middle most of the time. It is getting heated, reflecting. So every time it is pushed towards the middle of the box. And from the calculation also you will see it will come out at the middle. Means what we are expecting? We are expecting it to be at A by 2. So to start, we can start with the normalized wave function. The normalized wave function is psi n of x square root of 2 by a sine n pi x by a, okay, between 0 to a. Now the expectation value of x for this state will be minus infinity to plus infinity x, okay, Actually it is sin star x sin of x dx. This is the expectation value. So this, because this wave function is valid between 0 to a, so we can write it 0 to a x times psi n of x mod square dx. So on an average, where the particle will lie, anywhere between 0 to a, but where most likely to be found, it will come out to be at the middle. Let's see. So psi n of x is square root of 2 by a, so square of that, so 2 by a 0 to a x sin square n pi x by a dx. Now you see 2 sin square theta is equals to 1 minus cos 2 theta. We know this formula. 2 sin square theta is equals to 1 minus cos 2 theta. So we are going to utilize this trigonometric identity, and hence you get 1 upon a 0 to a x into 2 sin square theta 1 minus cos 2 theta. So 2n pi x by a and dx, right? So the first term 0 to a x dx is x square by 2 0 to a, and you see here if you calculate cos 2n pi x by a, so it will give you a by twice n pi sin twice n pi x by a, limit between 0 to a. So the value of sin at a and 0 is 0. So this second term is vanishing. First term remains 1 by a into a square by 2. So a and 1 a is cancelling, so a by 2. Okay. Look, we have made a mistake here. Although the final answer is okay, but here you see it will be little bit changed. X is multiplied na, so 0 to a x into cos 2n pi x by a. So we can use the integration by parts, and you will end up getting here 0 to a x cos 2n pi x by a. So the first term after applying the integration by parts will be 0, and you will get a by twice n pi whole square of it. Okay, so derivative of x is 1, integration of cos is sin, again integration, so cos, and minus plus minus. Okay, cos 2n pi x by a, now 0 to a. Now this is completed. You can use integration by parts, because here you will get 0 to a x cos 2n pi x by a dx. So if you take it as u, if you take it as v, the first term will cancel and the second term is written in this way, and if you put x equals to a cos 2n pi will be 0, and cos 0, sorry, cos 2n pi will be 1, cos 0 is 1, so 1 minus 1 is 0. So the second term, that is why it is 0. So what does it mean? You can see this expectation value is for general psi n. It includes n equals to 1, 2, 3 and all the values. So we can conclude from here that the average position of the particle is the middle of the box in all quantum states. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now can you tell me what will be the expectation value of momentum, means average momentum? What will be the average value of the momentum? Can you guess? Karthik, Murli, can you guess the expectation value of momentum? Tell me whatever comes into your mind. Momentum, remember, it is a vector quantity, right? Momentum depends on which direction the particle is moving forward. Now you see, this particle is moving, hitting, coming back, moving, hitting, coming back. So from the logic, you can say that the average momentum or expectation value of momentum should be 0, right? Let's prove it mathematically. What is the expectation value of momentum? Expectation value of position we have calculated. Let's not go for expectation value of momentum. And this is not only valid for ground state or fast acceleration, it is valid for any quantum state. Okay, for any value of n it is valid. So at all state, the particle is most likely to be found at the middle of the box. Now expectation value of momentum. To calculate that, we can simply put forward the formula. It is okay, I am just writing the main formula, minus infinity plus infinity psi n star x into p. P means minus I h cut del x. So d dx here one dimensional case, psi n x dx. So this is the general formula we can say. Now from sin star and sin, the root part, you see, minus I h cut. Let's write the limit, minus infinity plus infinity. Sin star is sin because the wave function is real, d dx of psi nx dx. Psi nx square root of 2 by a sin n pi x by a, this is equals to sin star x because this is real. So derivative of psi nx means derivative of this thing. What will it give you? Minus I h cut d dx of this. So 2 square root of 2 by a is coming twice, one for sin x, another for again this sin x, and n pi by a will come, and the limit goes 0 to a, right? Sin n pi x by a, and derivative of sin is cos n pi x by a. Another thing we have taken outside the integration. Now as you can see, this is sin a cos b. So if you take this square root of 2 square means 2 sin a cos b. So sin 2a, this is sin 2a formula. This is equals to minus I h cut n pi by a square. 0 to a. 2 sin a cos b means sin 2 n pi x by a dx, because 2 sin theta cos theta is equals to sin 2 theta. This formula we have used. This is equals to minus I h cut n pi by a square. The integration of sin is minus cos a by twice n pi cos twice n pi x by a limit 0 to a. So minus minus plus, what is it giving you? Actually we don't need to okay, let's do it. Minus minus plus, this a and this is cancelling, n pi cancelling, so I h cut by 2a. Cos 2n pi a by a, so this is cos 2n pi minus cos 0. Cos 2n pi is 1, cos 0 is also 1, so 1 minus 1 is 0. So you can see the expectation value of momentum is also 0. Why it is 0? Because the particle is moving in this way. So let's say if it has a momentum plus square root of twice m e, look, E is equals to p square by 2m, let's say. So p is equals to plus minus twice m e. So if it is going along this direction, the momentum is plus twice m e. If it is going along this, twice m e. And the particle is moving back and forth. It is going sometimes this direction, sometimes this direction. So there it is going in the equal amount in both the direction. So both direction plus twice m e minus twice m e, so that is 0. So logically also it is 0. Calculative wise we have just shown you here. Okay. Okay, so guys, we have to stop here. Actually, I have invigilation duty in the first half, so I have to go to college. For that, we have to stop here. Thank you very much for joining the session. I hope you find the session useful. You just try to revise. In the next class, we'll be solving problems based on this particle in a box, and we'll go for particle in a symmetric potential well. Then after symmetric, we'll go for finite, and it will keep on going. Thank you once again. Bye bye. Take care. Ending the session, guys.